presentation is present and future of OCT angiography. I would just want to share with you a few applications of today and to see what will be the future of this technology. As we have seen yesterday, we have seen that the evolution of the technology is increasing the number of A scans by second we can acquire, and the evolution of the technology is changing in one direction, increase the number of A scans. Due to the very quick evolution of the PC, we can accept all this evolution, and you can see that this is increasing, and we are changing our generation of machines very quickly. So, with moving to the Fourier domain, we have increased the rapidity of the acquisition of the systems, and we have known the first generation and the second generation of spectral domain OCTs, and now we are probably will move to source OCTs. But you will see that new technologies can probably improve OCT angiography in the next future, like, for example, OCT Doppler or adaptive optics. You will see a few examples. In these days, like the topic is today and tomorrow, in this day I will just want to share with you this kind of images. One team of the 15 Hospital in Paris are working in glaucoma, and they have noticed that we have few cysts in the inner nuclear layer, and probably we have a correlation with glaucoma. We have had a publication on this particular point in France, and so we are looking to the thickening of the retina in front of this cyst, and we can probably make a follow-up of these patients with OCT angiography in this kind of situation. It's a very thin cyst in this part of the retina, and you can observe in this case how it's appearing in this part of the angiography, of the OCT angiography, and in the deeper layer of the OCT angiography. And another example will be there. We have quite no response on the superficial layer, and we have a response on this layer. So it's very, very rare, but we can make a correlation with the glaucoma. Today, we can use for optic nerve follow-up, we can use a few tools, and these tools are proposed by OptoView at this time. The other competitors on OCT angiography have not yet software dedicated to optic nerve, but we have seen yesterday that all these tools are very powerful in quantification of the disease of the glaucoma and neuro-ophthalmology. This way of presenting the results have to be probably increased by using a large surface of analysis around the disc, and you have seen this kind of cards. We can use these cards on the macula, and when we move these cards to the optic disc, we can use this software in order to detect the reduction of flow density in different regions of the retina around the disc. And probably the future will be more precision and more analysis of this surface around the disc. And as you have seen on this one, probably only this ring is not sufficient to observe the modification of vascularization outside this ring. So the analysis will be probably more larger than we have now. As we have this relationship between reduction of vascularization around the disc and glaucoma, all the teams, all the engineering teams are working on this, and David Wang and Yalichka have published a few papers on this, and they are working with the idea to reconstruct in 3D the observation of the vascularization of the disc. As we have competition, when we only observe the fluid in the disc, we have competition with the big vessels and the very thin vessel around the disc, and so this approach probably will separate all the different vessels, and probably with techniques of subtraction of the big vessels in the analysis around the disc. They propose this kind of presentation with a 3D reconstruction and attenuation of the big vessels. Another evolution concerning this approach of the optic nerve, the vascularization of the optic nerve and vascularization around the disc, would be to move OCTs with a use like Doppler OCT. This will be an advantage to separate arteries and vein, and so you can see a few attempts of Doppler OCT. You can see that we can get many measurements around the disc, converted by many softwares, and go to this kind of presentation of the results. And we can color code these vessels. We can make a 3D reconstruction, and probably all the follow-up of the patients involved in glaucoma and ophthalmology can have benefit of this use of this system. But now it's very advanced research, and we don't have this in our current practice. Another very advanced system is proposed by Wolfgang Drexler, which uses a 3D Doppler. And you can see how we can reconstruct, even if these vessels are very small. We have published one work showing this kind of resolution of the Doppler, and probably in the next future, when we will have OCT angiography with coupling with the OCT Doppler, probably we will have information on the fluid inside the vessels. Going back to maps, you know that we have different maps we can use for follow-up of the patients, and you have seen many way of many approach of these different maps. One kind of maps would be to detect the non-perfusion area, and so we can detect it on the avascular zone in case of glaucoma, but we can detect it in diabetes, in the occlusion vein. And another evolution of this detection would be to observe the vessel density. This was a work proposed by Richard Rosen, and Richard Rosen have an agreement with OptoView, and probably you will be able in the software of OptoView to use this kind of maps. But we are just in a flat visualization of the retina and the values, and many of the researchers try to identify the different planes of the vascularization. And you have seen, due to the very powerful segmentation of OCT and OCT angiography, we can eliminate the superficial layer, the deeper layer, and the connection between both of them. And so you can see a work published by a French team concerning the color code of the arteries and the vein, and the color code of the very deep layer. You can see the deep layer, and if we are able to color code different layers of the retina, when we follow the patient, we can follow layer by layer the evolution of the treatments and the evolution of the pathologies. This is the kind of color code mark you can use, and you have see the interest in current practice with this neovascularization. But when we have this kind of images, the problem is we have quite the same compression of the information like in angiography. When we are in angiography, we take an en-face image, and all the layers are completely compressed. And when you show results of OCT angiography like this, it's the same thing. You don't know exactly where the different plane. In this case, we can color code vascularization in the choroid, in the chorocapillary, and we can color code the vascularization in subretinal position. And making this, if you join the box information, you can have a follow-up of the patients like this. And we don't know, when we treat a patient, when we treat a new vessel, we don't know which part of the neovascular region will respond first, or which part will grow up again. And so probably with this kind of approach that you have seen in the discussion this morning, that it's very difficult to have a standard acquisition. And so making this, probably we will have a way to observing the evolution of the different parts of the new vessel. As you have seen, and you have seen with these pictures, we can show you very, very clear pictures, very beautiful pictures, but false pictures. We can misinterpret many of these informations. And so the main point that will give us misinterpretation of the pictures and the OCT angiography is segmentation. Segmentation is a very, very high technology, working very well when you are in a perfect retina. When you have a perfect retina with differentiation of the different layers, this segmentation works with every machine. But when you have some disturbance of the layers, the technology is not sufficient. It's not at a level to separate a few different situations. And so another publication of Zhang, which we were working with David Wang and Yalijia, is to increase the way of separating the different layers of retina. And so they use any software in inverting the contrast and many software to get this kind of images. With this kind of images, they use the segmentation software, and they propose at this time a semi-automatic correction of the software. And you can see this box. In this box, we have misalignment of the segmentation. We can, with the help of the doctor, we can just put some dots in the right position, and the system will automatically correct the segmentation on this part. So this will be probably the future of the new machines and the new software in order to avoid some problems like this. They can use this software, and they have published this work in many situations, and you can see how it's difficult to get segmentation in these different layers when you have not a very flat plane. Many machines show you a very high level of segmentation when the different planes of the layer are flat. But when we have dissonance and when we have something like the cyst, it's very difficult. And you have seen this morning a few images. There was a discussion. We have seen that we don't know if we have a reduction of vascularization or we are measuring cyst. And so using this kind of software with help of the doctor, probably the machine will be more powerful. And please don't trust every image you see if you don't know how the image has been built. Another evolution of the OCTs will be to enlarge the line of acquisition. You know that the lateral resolution is dependent of the number of A scan on this line. And if you concentrate all this 256 line on 2 millimeters, we have a lateral resolution with a very high level. If you enlarge this 256 lines on a very large scan, you reduce the lateral resolution. So as we can increase the number of A scan, we can increase the length of the scan and keeping the lateral resolution at high level. You can see few examples of a spectralist module with this long scan, quite 16.5 millimeters. The goal of this is to increase the field of acquisition of lines, but in consequence, the enlargement of the acquisition of OCT angiography. One another attempt is Canon. I've shown you these images. And the Canon system, this is just a previous step of the Canon system, and they can yet give you information with OCT angiography, including optic nerve and foveolar region. And you can see that probably the next future we will have this solution. Another solution to enlarge the visual field, the field of acquisition of OCT angiography, will be to create mosaics. You can see one example of mosaic with the OptoView system, and so you get few acquisition, and with an automatic software we can recognize the vessels, and the machine will reconstruct the advantage of this system is we can be perpendicular to the globe in each part of the acquisition. With a long scan, with the curvature of the globe, we probably have this problem with the reconstruction of this curvature. We make this always on the right position, on the right plane. So probably both systems will be competition for the next future, and probably that will be combination of the both. Another solution could be this attempt from Wolfgang Drexler from Vienna. He has published a large acquisition of OCT angiography with a research system, and you can see the first attempt he has shown with a sufficient resolution to zoom on this part. You can see the zooming of this part, and so the resolution is so high we can zoom in different parts, but have the information on this large acquisition zone. Another step you have seen is increasing resolution. As the systems are more and more efficient in acquisition, in segmentation, in treatment of signal for reconstruction of the vessels, the more we increase resolution, the more we can see details, and the less we have artifacts or misreconstruction of the vessels. And this is one image of the Canon system with a 2-micron resolution focused on the optic nerve, and you can see that this evolution can show you, this image is probably movement inside the vessels to explain these little dots inside the vessels. But in terms of resolution, we can go with a higher resolution more when we go to the adaptative optics. And we have in France a company which name is Imaginai, which have built an OCT improved by adaptative optics. And this kind of resolution can show you this kind of images, and you can see the fibers just on the ring of the optic disc. And if we put the focus on the big vessels, we can observe this kind of images. Right? We can observe this kind of images. And so now they plan to follow patients. The problem with this kind of images is we have a very thin focus zone, and we don't have a very large exploration. So when we know that there are a problem, we can use this focus and this very high level follow-up of patients on a specific area. And so probably combination of these images and OCT angiography will be one another way to develop our knowledge of this part of the exploration of the eye. And so you can see that we have many new works to do. It's just the beginning. OCT angiography have been put in the market since most 1 year with few machines. Now we are many more machines, but it's just the beginning. And so you can see that this new technology arrived in our current practice with just few machines, but the evolution of technology will push this technology in every center, in every big center at the beginning, and probably in many other centers after. So that has been a great pleasure for me to share with you all these days and all this information. So I hope that probably in September, if you want to come in Paris, we have to share many other informations. And I have to thank you very much, the organizing committee, and Professor Claude, and all the guys out there. Thank you very much.
you very much. Are there any questions from the audience?
Thank you for your presentation. Flow density and retinal nerve 5 layer is associated or correlated when you determine glaucoma or not glaucoma. I mean, with OCT A and when you use normal standard OCT to check retinal nerve 5 layers and compare with flow density and it correlation or.
In fact, we try to observe one mechanism, which is reduction of vascularization around the disc. So you have many ways to approach this, and you can detect the key point, which is the reduction, and so you can detect the zone of non-perfusion, and you can detect the flow density or the vessel density to observe a negative part, and you can observe what is not working in this part. Okay? It's two ways to saying the same way. But probably we will have more and more if we have dogma with this.
Thank you.
Any other questions? I guess everyone's very eager to go on to the case discussion. So thank you very much. And I'd like to invite the faculty to come on stage to begin the case discussion.